Hi, this is our Group Lab 6 demo video. I'm going to talk about our group CUDA programming project, which explores matrix multiplication performance using different optimization methods on GPU. We will go from the basic CUDA implementation to the optimized tiled version and compare their performance with the CPU version and the Kubernetes library. And in the second part, we implement and accelerate a convolution function for image processing. First, we write a C program that applies an n by n filter to an m by m image, testing several filters such as edge detection on sample images and collecting performance data for different sizes. Then we port the convolution to CUDA to utilize GPU. And finally, we integrate the CUDA function into a Python shared library. Our team worked in an equal and collaborative way. Everyone contributed to different steps of the project, such as testing the CPU code on our own laptop, configuring the Google Cloud instance. Whenever one member faced a problem, others provided guidance and support. First, we implemented a CPU version using plain C loops. These three nested for loops to do the matrix multiplication and see the runtime. Yes, this is the result runtime. Three different sizes, three different runtimes. However, we need to know that game laptop CPU is so powerful, so that the GPU on the Google Cloud cannot beat it. So we implemented our C program on Google Cloud virtual machine again to make sure our comparison more rigorous, and this is the runtime on Google virtual machine. The CPU version uses the same data size, so we can fairly compare the result. Next, we do the CUDA programming. We implement the naive CUDA kernel for matrix multiplication. This is the code. These are the codes. Each thread computes one element of the output matrix by iterating through all elements in its row and column. We calculate the row and column of each thread using these two variables. We wrote this here. Then each thread performs an entire dot product between one row of matrix A and one column of matrix B. That means every thread reads many elements directly from global memory, both from A and B, for every single multiplication. However, this version doesn't use shared memory, so every multiplication reads directly from global memory, which is quite slow. Because global memory has high latency and low bandwidth compared to the on-chip memory, so the GPU spends most of its time waiting for data instead of doing calculation. And these are the results of different matrix size, and this is the runtime. Next, we followed the instructions to build a Google Cloud instance. Choose the CPU version, to choose the GPU, VM version, and the machine type. And this is the virtual machine we created. So after creating this, we tested the naive CUDA version on the Google Cloud virtual machine with different matrix size, and we recorded the runtime. The result shows that as matrix size increases, performance improves up to a point because more GPU threads are efficiently utilized. We can see this. We made a runtime table to show the different runtime between C CUDA program and the optimized CUDA program. So after that, we will show that. Okay, after the this is a screenshot. These are the screenshots that we created a virtual machine. Okay, after a naive CUDA program, we do the this is the steps that we set up the environment of the virtual machine and run the naive CUDA program. Those are the screenshots. After naive CUDA program, we introduced the shared memory optimization, also called tailoring. This method divides the matrices into smaller 16 by 16 tiles. Let me show the code here. Okay. This method divides the matrices into smaller 16 by 16 tiles that are loaded into fast shared memory. Each tile is reused multiple times before moving to the next, which greatly reduces global memory access. Each thread block computes a small tile of the result matrix. For example, a 16 by 16 tile. Before performing the computation, each block first loads a corresponding 16 by 16 submatrix of A and B into shared memory. These two lines. And since the shared memory is on chip and much faster, data can be reused by multiple threads within the same block. So each tile of A and B is read-only once from global memory, but reused tile waits time during the computation. So the results. So those are the results of the tiled version matrix multiplication. We can see that the result. We can see that we have the 2 times to 4 times speed up compared with the naive version and the CPU version, confirming that shared memory makes a big difference. This is the timetable. This is the table that we recorded each implementation on CPU, naive CUDA, and optimized CUDA, and with different matrix size and its runtime. And we can see the speed up is very huge. Sorry, I made a mistake. The result showed that the 2 times to 4 times speed up compared with the naive version, with the optimized version, and these data are compared with the CPU version. So we can see maybe 200 times and 400 times, but the optimized CUDA is 2 times to the 4 times faster than the naive CUDA version. So as we can see, the GPU acceleration provides massive speed ups over the CPU, up to several thousand times faster for large matrices. The speed up is greater than 1 means that the GPU is faster, otherwise the GPU is slower.
Okay, in part 6, so far we have implemented 3 versions of matrix multiplication. The CPU version, the naive CUDA version, and an optimized CUDA version using shared memory tiling. So in part 6, we go one more step and using NVIDIA's high-performance linear algebra library, which is called lab6. Here we use the function lab6sgen, which means single precision matrix multiplication. This call replaces our entire kernel and automatically handles tiling, memory accessing, and scheduling optimization on the hood. So we run the code in the cloud and we can get the results. So the table shows the results of the 4 versions of CUDA code. This shows how powerful the vendor optimized libraries can be. They save us time and give near peak GPU performance. After that, we go to part 7. In part 7, we take our optimized CUDA kernel from part 5 and modify it so that Python can use it as a shared library. The kernel function matrix multiply tiled stays the same. It still uses shared memory tiling for performance optimization. What we actually modified is the program structure. We added a C-style wrapper function named GPU matrix multiply. Okay, in this function, it handles GPU memory allocation, data transfer, kernel launches, and copying the results back to the host. Frees the memory. Okay, and it's a Python code which we can use in C types, wrote the library and run it. So we define the arguments types with numpy arrays and call GPU matrix multiply. And here we get the result. For example, with n equals 1024, the Python call to the code library completed in about 0.36 seconds, which is slightly slower than running the CUDA executable directly, but still much faster than the CPU version. The small overhead mainly comes from the Python to C interface, not GPU computation itself.
Hello, I want to talk about our lab6, and I'm doing the part 2, which is about implementing the convolution function on C. So first of all, we're doing something like this. This file is about like we use different kernel to do the edge detection for a single image, like this image. And what we do is use different kernel to swap all of the metrics in this image and try to output the output image and at the runtime. Here's the result. Because we use the same size kernel, the time is close, And here's a different kernel result. We use lab6, which you can detect the X layer, the horizontal edges, and lab y, which you can detect the vertical edges, and lab6, which you can, and Gaussian is to avoid the noises. The second part we do is to we have a function to try to compute the runtime of different picture sizes and different kernel sizes, and what's the difference between their runtimes. So this is our function, and we use this function to use as a default size. We use a 3 multiplied 3, and we can use different input to the script and get a different runtime. So and the next part we try to coding those things on the CUDA, and we do the same things here, and we write some CUDA coding like this to try to copy our kernel and image to the CUDA kernel, and we do the same thing and test the runtime by naive CUDA. So here's a difference. We try 3 different N and M. First is we use 1024 multiply 1024 image and 3 multiply 3 kernel, and we have the runtime like this. And we try a different thing like 2048 multiply 2048 image, and 5 multiple 5 kernel, and we have a runtime like 1 millisecond. And we use 2048 size kernel, size image, and 3 size kernel, and we have this runtime. The next thing is we try to build this CUDA file to an SO function, to which we can direct from our Python project. So here we can we get this .so library, and we can try to use it in our Python. So here we got the library, and we do the same thing. We can use a kernel to do all the same thing and output the runtimes. So here we got the result. We use the same size. We never change. We didn't change the size. Which we can compare so that we can compare the result, like the efficiency of different languages, and like the CUDA or the C. So this is our output and the runtime difference. And we have a list. Sorry, we have a matrix here, and this is what we used. And this is for the image size. This is kernel size, and those are the runtime. So we can see CUDA at the same size kernel and the images. CUDA is always significant faster than the C. And if you use Python to use the lib from your CUDA, it will be more faster, and that's what we want. And so here we have 2 pages for the runtime, and here we can see how significant runtime faster bytecode. Yeah, so that's all the thing we use to we build in the part 2. Thank you.